Hello, today we're going to continue in our series on particle physics, looking at angular momentum and spin. First, a health warning. Whenever we talk about angular momentum and spin, the problem is that we tend to think of classical things, like a spinning top or a spinning ball. And to some extent, that gives us an understanding of what we mean when we talk about things happening in quantum mechanics and angular momentum and spin. But that analogy, the classical analogy, only goes so far. And we shall see that when it comes to quantum mechanics, all is not as it seems. So let's start by thinking about a ball. Here's a ball, and we can spin it. We can spin a ball on any axis, but it has to have some axis, so let's have an axis there, and we spin it with a rotational velocity omega. And we say that that spinning ball then has an angular momentum, and the angular momentum vector points along the axis of the spin. And the direction of the axis is given by the corkscrew rule. So you look at the way the ball is spinning, and if it is spinning clockwise, then rather like a corkscrew, if that is spinning clockwise, the arrow goes in, or the corkscrew goes in. If it's spinning anti-clockwise, then the arrow would be in this direction. So that's an object which spins on its own axis. It has angular momentum. We sometimes call that spin. A different type of orbital motion is, for example, when the Earth goes around the Sun. This is the Sun, here is the Earth, which goes in almost circular motion around, to be accurate, around the centre of mass between the Sun and the Earth, but the centre of mass is inside the Sun itself. So the Earth goes around the Sun, and that is orbital motion, and that is orbital angular momentum. And once again, the angular momentum vector will, in this case, come out of the page because I've got it that the Earth is going round anti-clockwise. Now I just want to remind you of what we've shown, a diagram drawn several times before and doubtless will be drawn again. The problem of an electron orbiting a nucleus. There's the nucleus, there's the electron. And what we said was that if you think of that electron as a particle orbiting, it is essentially accelerating as it orbits, and an accelerating charged particle would radiate energy away, and as a consequence it would spiral into the nucleus and the whole atom would disintegrate. And that was a major problem, but it was quantum mechanics that comes to our rescue and says that you don't think of the electron circulating or orbiting as a particle, rather you think of it as a wave. And so you've got this electron wave which is going around. And the point about that wave is it's a joined up wave. There is no disjoint between where it starts and where it ends. And that means that there is a whole number of wavelengths in that orbit. So that there are n wavelengths where n is a whole number, an integer, in the circumference of the orbit, which is 2 pi r, where r, of course, is the radius of the orbit. And then we remember the de Broglie formula that lambda equals h over p. And so we put lambda into here, and we've now got that nh over p is equal to 2 pi r. And from that you can see that pr is equal to nh bar, where h bar is h over 2 pi. And pr is classically what we call angular momentum. It is the orbital momentum or the linear momentum times the radius. So if you've got the electron having momentum p going in that direction, then you multiply p by r, and that gives you the angular momentum, which you will now see is in integer units of h bar because n is an integer. What that means is that angular momentum cannot just take any old value, it has to be in units of h bar. So if you've got an axis that is like this, we'll call that m h bar, where m is a number, a whole number, integer. Then if you move it on a bit, if you give it a little bit more angular momentum, then it will have m plus 1 h bar, and if you give it less angular momentum, then it will be m minus 1 h bar. The key point being it cannot have any value between these. They are step changes because angular momentum comes in units of h bar. And then we just want to clarify what we are talking about when we refer to spin and angular momentum. There is a spin, which is essentially a spin on your own axis, rather like the spinning ball that we talked about earlier. So we can represent that as a spin that goes around like this. It's just going on your own axis. And that's called spin, and we give that the letter S. Then there is the orbital motion, where let's say we've got a vector like this, and it simply goes round some central point, but you'll notice that the vector doesn't change direction, so it's just going round but keeping in the same, pointing in the same direction, and that we call orbital angular momentum L. And then there's finally an angular momentum where the vector itself spins on its own axis and goes round some central point. So now the vector is going round like this, and that's obviously a combination of spin and angular momentum. We call that J, and J is clearly going to be equal to L plus S in vector terms, because J is both a spin on your own axis plus an orbit around some central point. Now, from a classical mechanics point of view, the angular momentum vector L, which is what we're going to look at first, is equal to the radius vector cross product with the momentum vector. And the radius vector, of course, can be given its coordinates x, y and z, and the p vector will have coordinates px, py and pz. And now these are just definitions of the cross product. This is nothing to do with quantum mechanics now. We're simply doing a definition that the x component of the angular momentum is given as ypz minus zpy. So it's the y coordinate of the radius times the z coordinate of the momentum minus the z coordinate of the radius minus the y coordinate of the momentum. And that's the only thing you need to learn, x, y and z, and then you spin these two round the other way for here. And if you want the other two, all you have to do now is cycle. So Lx, next one is y, Lz equals, and now cycle from y, so that's going to be yzx. Here you're going to cycle from z, so that's going to be px, py. The minus terms are always the same. Cycle from z, you get x, y. Once you get to z, you go back to x again. Here you cycle from y, so that's going to be pz, px. And those are the three terms which identify the x, the y and the z coordinates of the angular momentum in terms of the x, y, z coordinates of the radius and the px, py, pz coordinates of the momentum. Now a little reminder about what we called the commutator of x with p. The commutator of position and momentum, that's p. We showed in the videos on quantum mechanics concepts that that equals IH bar, which of course means it does not equal 0. And the significance of that is that if you want to measure two objects at the same time, if you want to make two measurements at the same time, their commutator must equal 0. If it doesn't equal 0, you can't measure them simultaneously. And that's how we showed the Heisenberg uncertainty principle, that you cannot measure position and momentum at the same time. Now I should be a little more precise about this, because I should give this the subscript x. You cannot measure the x coordinate and the px coordinate of momentum at the same time. You can measure the x component of position and the y component of momentum at the same time. That commutator does equal 0. So it's only when you want to measure the position and the momentum in the same coordinate that you come unstuck. And just to be clear, of course, there's nothing to stop you measuring the X and the Y component of position, or indeed the Z component, at the same time. And there's nothing that stops you from measuring the PX and the PY, or indeed the PZ component at the same time. So you can measure any two coordinates, or indeed any three coordinates of position, any three coordinates of momentum. You can even measure the X coordinate of position and the Y coordinate of momentum. The only thing you can't do simultaneously is to measure the X coordinate of position and the X coordinate of momentum. With that in mind, therefore, I now want to ask the question, can you measure the X coordinate of angular momentum and the Y coordinate of angular momentum at the same time? If you can, then the commutator must be equal to 0. So we need to find out what this commutator is. Well, the definition of a commutator, you will recall from the quantum mechanics concepts videos, is that Lx, Ly, the commutator of Lx, Ly, is simply defined as Lx, Ly minus Ly, Lx. And I remind you that if these were simply numbers, they would be bound to equal 0, because 2 times 3 minus 3 times 2 is 0. But what I'm going to do is to take these terms and substitute for them the values that we've got here and here. So I'm going to substitute these two terms for Lx and Ly. So that's going to give me ypz minus zpy times zpx minus xpz minus, and now we've got this term, so that's Lx, that's Ly. Now I've got to put minus Ly, which is zpx minus xpz, times Lx, which is ypz minus zpy. Now, although that looks rather horrifying, you'll agree, won't you, that essentially you're going to get, from this product here, you're going to get 4 terms. And from this product here, you're going to get 4 similar terms, except that at this term, these two terms here have been swapped around. So the numbers are just going to be in a different position. So let's have a look at, let's say, this term multiplied by this term here. So you're going to get a y, px, pz, z. And then here you're going to get a similar term, z, px, y, pz. So what you're going to get is y and px, which of course commute, so you're not going to have any problem with that, because there's no problem about measuring y and px. But then you're going to get into pzz minus zpz. Right, y, px, pzz will come from that product. Y, px, z, pz comes from this product, the similar product here. And the point is that pzz minus zpz is the commutator of pz with z, and that is not 0, because you can't measure them both in the same at the same time. And that comes out to be minus IH bar. Incidentally, I've just spotted an error further up the page here. The commutator of xpx is not minus IH bar, it's plus. I hope I will have put an annotation to that effect as soon as I made the mistake. But that should be plus IH bar if you do x with px. So consequently, if you do pz with z, because this is actually the commutator pz and z, you get minus IH bar. Okay, now let's do these two. So that will be those two terms there. That will give you xpy, so minus times minus will give you a plus, so that's plus xpy into zpz minus pzz. Right, so you've got you're going to get an xpy, from these two terms you're going to get an xpy z times pz plus an xpy pz times z. So you're going to get that term there, and that again is the commutator of z and pz, and that is plus IH bar. When you look at the other two terms, you will find that there is nothing in them that's going to cause you a problem in terms of commutation. They are all going to equal 0. Here you've got yx pz squared. Well, that's no problem, because when you get the same term from this multiplier, there is no commutation problem. And so the two will just simply vanish. One minus the other will equal 0. And similarly for the fourth term. So the only two terms where you will have a commutator problem are the two that we've already identified. So that is going to be minus IH bar ypx plus IH bar xpy. I can take the IH bars outside, so I've got IH bar into xpy minus ypx. But xpy minus ypx is LZ. So this is simply equal to IH bar LZ. So we've shown that the commutator LX LY is equal to IH bar LZ, which of course does not equal 0. Consequently, you cannot measure the angular momentum along the x-axis and the angular momentum along the y-axis at the same time. And just for completeness, let's just write down what the commutators are. Lx, Ly, as we've just shown, is equal to IH bar Lz. Ly, Lz commutator is equal to IH bar Lx. All you're doing, you'll notice, is cycling x, y, y, z, zx. So Lz Lx is equal to IH bar Ly. So those are the three commutators, and what they essentially say is that you cannot measure more than one coordinate of angular momentum at any one time. By convention, we choose to measure the coordinate of angular momentum along the z-axis. Of course, it doesn't really matter which one you choose, but we, by convention, choose z. And in doing so, we abandon all hope of ever knowing what is going on angular momentum-wise along the x and y coordinates, because as we've just shown, you can never know. If you know what's happening, if you know what Lz is, the angular momentum along the z-axis, you can never know what's going on along the x and the y coordinates. So here is my spinning ball, as it were. There's the axis, which we'll call m. And what we're going to do is to measure that angular momentum, but along the z-axis, or the z-coordinate. You remember we said that it's quantized, which means the next notch up will be m plus 1, and you measure that along the z-axis. One down would be m minus 1, and you measure that along the z-axis. The point being that having measured the angular momentum along that z-axis, you can never know what is happening along the x and the y-axis. Now I want to create two new terms, L plus, which I'm going to call Lx plus I Ly, and L minus, which I'm going to call Lx minus I Ly. I'm not going to tell you what they are, L plus and L minus, though you may be able to guess. We'll see what they are in a moment. And the first thing I just want to check is what is the commutator of L plus and Lz. This will tell me, of course, if I can measure L plus, whatever it is, and Lz at the same time. Well, that, of course, is just the same as the commutator Lx plus I Ly, because that's what L plus is, with Lz. And we know what that is because the commutator of Lx and Lz is minus IH bar Ly, because it would have been the other way round if you wanted it to be plus IH bar Ly. And the commutator of Ly and Lz, we've got an I here, so let's put that I first. The commutator of Ly and Lz is IH bar Lx. This time it is plus. And so that's going to give me, these two i's multiplied together will give me a -1. So that means I've got two minuses. I can bring the minus and the h bar on the outside. From here I'm just going to be left with Lx. From here I'm going to be left with plus ILy. And those shouldn't be, that's not a commutator, that should just be round brackets. So I've got minus h bar into Lx plus ILy, but Lx plus ILy is L plus. So that equals minus h bar L plus. So I've shown that the commutator L plus and Lz is equal to minus h bar L plus, which does not equal 0, which as it happens means you couldn't measure these two at the same time, even if you wanted to. And I can also tell you, without going through all the maths again, but you can do it, check it if you wish, that the commutator L minus Lz is equal to plus h bar L minus. So that's the other commutator here. Now, let's just think about what Lz actually does. Lz is an operator. And Lz is going to act on the state of the system, which is, for our purposes, the state of angular momentum of the system. And what Hermitian operators, which are measurables, do, we've learnt this many times in quantum mechanics concepts, is they act on the state of the system to provide an eigenvalue. And the eigenvalue, of course, the actual value you're going to measure, is the value of the angular momentum along the z-axis. And of course it is multiplied by the eigenvector m. That's a form that we've had many times in quantum mechanics concepts. If you don't recognise it, you really do need to look at that series, because everything I do in this series is based on assuming you know the quantum mechanics concepts. So the operator Lz acts on the eigenvector m, which is the state of the system, or particularly the state of the angular momentum of the system, and it gives you back the same state, but it gives you a measurable now, which is the actual measurement of the angular momentum along the z-axis. Okay, so what happens if you take L plus and you act on m? That will give you some new eigenvector, some new state. We don't know what it is yet, that's what I want to try and find out, but that is now a new state. So let's measure it. And of course we measure it along the z-axis using the operator Lz. So I want to know, when I operate on the state m with L plus, I get a new state, and then I measure it with Lz. Well, what's that going to give me? Well, I just want to remind you that we showed you that the commutator of L plus with Lz is minus h bar L plus. So I can just write down here that L plus Lz, the commutator thereof, which is, of course, the same as saying L plus Lz minus Lz L plus. That's what a commutator is. And that equals minus h bar L plus. So rearranging this here, I can say that Lz L plus, which is that term there, is equal to L plus Lz, that term there, plus h bar L plus. And what we typically do in this arrangement, as we've done so many times before, is we set h bar to 1. Sorry, you may not be able to see that. H bar equals 1. And what that does is it gets rid of all the constants so that we don't clutter up the formulae. So now what I can do is to say that here I've got Lz L plus acting on m, but for Lz L plus I can write instead this term here, which is L plus Lz acting on m, plus, h bar is a 1, so forget about that, so that's going to be plus L plus acting on M. And what I want to know is, what is that? Well, when Lz acts on M, it simply gives me back the eigen value M. Lz on M gives me M on M. So this is now just L plus times M on M plus L plus M. M, of course, is just a number that can come on the outside. So now we've got M plus 1 all acting on this term, this new state of L plus M. And so you've got the answer, that Lz acting on L plus of M gives you M plus 1 acting on L plus of M. M plus 1 is the eigenvalue. In other words, what L plus has done is it's moved up the angular momentum from M to state M plus 1. L plus is therefore the promotion operator, if you like. It's the operator that shifts the angular momentum by 1 notch, by 1 amount of h bar, to get up to the next value. And you won't be surprised to know that if L plus is responsible for shifting the angular momentum up by 1 notch, L minus is responsible for shifting the angular momentum down by 1 notch. Now the question is, can L plus and L minus act for an infinite number of occasions? Remember, we are measuring along the z-axis. So here is my angular momentum, we'll call that M, and we measure it along the z-axis. Along comes my operator L plus, and L plus simply notches the angular momentum up by 1 notch. So that's now M plus 1, which again we measure along the z-axis. We keep applying L plus. How far can we go? Well, we can go up to the point at which the angular momentum is wholly aligned along the z-axis, at which point we will have reached a maximum value of M. And now if you try to apply L plus again, you can get no result. It's just not applicable, because once you've got to the maximum value, which is when the spin or the angular momentum is aligned with the z-axis, which is the axis you're measuring against, that's the maximum value of M. And L plus can have no further effect. Similarly, if we act with L minus, that will take us down a notch. And we can keep acting with L minus until the angular momentum is now aligned in the opposite direction along the z-axis. And at that point, we measure a minimum value of M. So all the way down this Z scale, we have got quantized values of measurements of the angular momentum, subject to the fact that there's a maximum value when the angular momentum is wholly aligned with the z-axis, and a minimum value when, as it were, it's anti-aligned, it's aligned in the opposite direction with the z-axis. So if you look at that z-axis, you will find that there's a maximum value of M, there's a minimum value of M, there'll be what one might call a 0, that will be a plus M, that will be a minus M. There's a 0 value which effectively accords when the angular momentum is aligned along either the x or the y direction, you don't know which, but it's essentially perpendicular to the z-axis. And so there are M values in here and there are M values here plus the 0. That means that there are a total of 2M plus 1 possible states of angular momentum, and they are each quantized because the states come in units of h bar. L plus will shift the angular momentum up 1 notch, subject to the fact that once you've got to the maximum, L plus has no more effect. L minus will move you down a notch, subject to the fact that once you're at M minimum, L minus can have no further effect. Now from Pythagoras, we can simply say that the total angular momentum squared is going to be the coordinate along the x-axis squared plus the coordinate along the y-axis squared plus the coordinate along the z-axis squared. It matters not that you can't measure all these three things simultaneously. The fact is Pythagoras requires that that must be so. That's just geometric. So let's just do a little bit more manipulation. I want to find out what is the product L minus L plus. Well, that by definition is going to be Lx minus ILy, which is L minus, times L plus plus ILy, which is L plus. And if you multiply those out, you will get that Lx times Lx is Lx squared. Minus ILy times plus ILy comes to plus Ly squared. And then these two terms together will give you plus ILx Ly minus ILy Lx. And this term here is simply plus I into Lx Ly minus Ly Lx, which is I into the commutator of Lx with Ly, because that's what that is, that's the commutator. And we know what the commutator of Lx and Ly is. It's IH bar Lz. Now we set h bar equal to 1 in our usual fashion, so that gets rid of the constant that would otherwise be in the way. I times I is minus 1, so this just becomes minus Lz. So the L minus times L plus is Lx squared plus Ly squared minus Lz. And that means that L squared, which you'll remember we said was Lx squared plus Ly squared plus Lz squared. Well, there's the Lx squared plus Ly squared. So L squared is going to be equal to L minus times L plus, which gives us Lx squared plus Ly squared minus Lz. Well, the minus Lz is no good, so we better get rid of that by going plus Lz. And that just gives us now Lx squared plus Ly squared, but we also need an Lz squared. So we've now got that L squared, which is of course Lx squared plus Ly squared plus Lz squared, is the same thing as L minus L plus Lz plus Lz squared. So when we act with L squared on our state M, and we'll make that the maximum value of M, so we'll call that M max. That is the same as saying L minus L plus acting on MM plus Lz acting on MM plus Lz squared acting on MM. Okay, because L squared is simply this, and L squared acting on M is each of those terms acting on the maximum value of M. But what does that actually do? Well, let's start off by thinking about this term here. When you've got a product of operators, it either acts entirely or not at all. Here we've got an L plus acting on M max. What does L plus do when you are already at the maximum? Nothing. It cannot do anything at all, so that term there equals 0, because the L plus can have no effect. What does Lz acting on M produce? MM, that produces M times MM. It's the eigenvalue. It's the maximum value of M. So I can call that MM. And what does Lz squared do? Well, that of course just produces MM squared acting on MM. Lz will always return the value of the angular momentum along the z-axis. So Lz will return the maximum value because we are at the maximum, and Lz squared will simply return the square of that. And that gives us therefore that L squared acting on the maximum value of M gives us M squared maximum plus M maximum acting on, all of that acts on mm. Lz squared acting on mm would simply give you m squared acting on m. Right? So if you have the maximum value of angular momentum, which means the angular momentum is aligned with the z-axis. Let's go all the way back up here to the diagram I drew. When the z-axis is aligned, when the angular momentum is aligned with the z-axis, you get the maximum value of angular momentum along the z-axis, because that's the only thing we can measure against. And when you measure that, Lz, which is the operator, will simply return you the eigenvalue of the angular momentum, which is the maximum value of m. So that's what we've got down here, that Lz squared returns m, the maximum value of m squared. No problem. But when you measure the total angular momentum, what do you find? The maximum value squared plus another bit, another mm, another m max term. Now this is where quantum mechanics and classical mechanics part company, if they hadn't already. Because if you measure the angular momentum along the z-axis when the angular momentum is aligned with the z-axis, then the total angular momentum would be along the z-axis. In other words, all of the angular momentum is along the z-axis, classically. But quantum mechanically, when you measure L, you get what you would expect to get classically, which is the m max squared, plus a little bit extra. And where does that little bit extra come from? Well, that is what is the residual angular momentum, which is somehow distributed between the x and the y coordinates of the angular momentum that you can never measure individually because you are forbidden. We've shown that you cannot measure more than one coordinate at a time. So what we're saying is that unlike the classical position, when angular momentum is wholly aligned along the z-axis, quantum mechanically, there remains an amount equal to m max, which is distributed between the x and the y coordinates, and you can never measure it. You know that between them there is m max, but you don't know how it's distributed, and you never can. And if you think about it, that must be true. Because if the angular momentum were wholly assigned to the z-axis, and you measured it, then you would know that the angular momentum measured along the z-axis was m max, and that the angular momentum along the x and the y coordinates were 0, and that would mean you would know the angular momentum along the z, the x and the y coordinates, and you're not allowed to do that. And this is the way quantum mechanics, as it were, undermines your ability to get round it. It says, yes, when you measure along an axis which is aligned with the z-axis, yes, you will indeed get m max squared, which is what you'd expect to get when you measure Lz along the z-axis. But there's a little bit extra, which is still being distributed and which can never be aligned wholly along the z-axis. A little bit extra is still distributed between x and y to provide an unknowable that you can never know precisely in terms of how it's distributed. And if we think back to the third video that I did in the quantum mechanics concept series, when you remember I said that we could align the spin of an electron in any direction that we chose simply by putting it through a magnetic field. And I said, let's suppose we align the spin of the electron so that it is wholly along the z-axis. And then we measure, if you remember, we measured it using a device with red and green lights which told us whether the spin was up or down. And I said that if you aligned the spin entirely along the z-axis, you got 100% of all those electrons would measure up. What you may have inferred, but what I was very careful not to ever say, was that all the spin is wholly along the z-axis. And that is not, of course, true. What we've just shown is that you can certainly align the spin along the z-axis. There's no problem about doing that. And that will give you the maximum value of spin along the z-axis. But when you do that, there is still a residual amount of spin that is somehow shared between the x and the y-axis. And you can never measure what that is. You know what the total value is shared between the two, but you don't know how it's distributed. So what I now want to know is, can you measure L squared, that is the total angular momentum squared, and the angular momentum along the z-axis at the same time? If you can, that commutator must equal 0. Well, we showed that L squared is L minus L plus LZ squared plus LZ. That was what L squared actually is. And what I want to know is, does that commute with LZ? Well, this of course will need to act on a state, so let's have it acting on the maximum value of M. And what happens now? First, we've got this term here acting on the maximum value of M. What happens when L plus acts on the maximum value of M? You get nothing. So that term goes. What happens when LZ squared acts on the maximum value of M? It returns the eigenvalue of mm squared. What happens when LZ acts on the maximum value of M? You just get mm. And similarly here. These are all numbers. These are eigenvalues, real numbers. All real numbers commute. Consequently, this commutator equals 0. And that means there's absolutely no problem about measuring the total angular momentum squared and the angular momentum along the z-axis at the same time. And that's why, as I say, if you measure the total angular momentum, you will get m max squared plus m max, whereas if you just measure the LZ component squared, you will get m max squared. It's that little bit of extra angular momentum embedded in L squared that is distributed along the x and the y coordinates, just to maintain the uncertainty about exactly where the angular momentum is. Now I want to focus on spin as such, and a lot of this has been covered in the first 3 videos that I did in the series on quantum mechanics concepts, so I refer you to those. But I remind you that one of the things we said was that if you measure, remember, if we put electrons through this device here and measure the spin, you can only ever get 2 answers. You can have this box aligned in any way you like, but however you align the box, you can either get 1 or 2 answers. Either you will get an up spin or you will get a down spin. And so those are the only 2 options, up and down. And what we do is we assign angular momentum values or spin values of half h bar and minus a half h bar. And why do we do that? We do that because we said that the difference between 2 states comes in quantized values of h bar. And the difference between plus h bar and minus h bar is, of course, h bar. So that's the reason that we give it plus a half and minus a half, because they each have symmetric values. And the difference between the 2 is a whole value of h bar. And just as with angular momentum, so it is true of spin, that you cannot measure the spin along the x-axis and the y-axis at the same time. The commutator is IH bar SZ. The commutator of SY is SZ is IH bar SX. And the commutator of SZ with SX is IH bar SY. That's exactly the same as what we've just shown for angular momentum. Just as you cannot measure angular momentum along more than one axis, so you cannot measure spin along more than one axis. We showed in the videos on quantum mechanics concepts that you could represent the spin state of a particle, electron, whatever, as a combination of a probability amplitude for it being up and a probability amplitude for it being down. This is the probability amplitude that you'll get an up. This is the probability amplitude that you'll get a down. To get the probability, you have to square the probability amplitude, or more accurately, multiply by its complex conjugate. So the probability of getting an up will be alpha alpha star, where alpha star is the complex conjugate. And the probability of getting a down is beta beta star. And since you must get either an up or down, you never get a zero, you always get one or the other. That means that the probability of up plus the probability of down is equal to 1. So consequently, alpha alpha star plus beta beta star always has to equal 1. That's called normalization. And what are these spin operators, Sx, Sy and Sz? Well, we've actually already done this in quantum mechanics concepts. Sx is nothing more than the Pauli matrix sigma x, which you'll remember was 0, 1, 1, 0. Sy is the Pauli matrix sigma y, which is 0 minus I, 0. And Sz is the Pauli matrix sigma z, which was 1, 0, 0, minus 1. So we have effectively already covered the values or the measurables, the operators Sx, Sy and Sz. And that equates to, if you remember our device, if you place it so that you're measuring along the z-axis, you will get an up or down. If you place it so that you're measuring essentially along the x-axis, again you will still get up or down, but up in this orientation is right and down is left. And if you, as it were, have it going into the page, I can't easily draw that, but you have to imagine that that is pointing into the page, then up will be in and down will be out. So on the 3 dimensions, you either get up or down, left or right, or in or out. And we showed that the eigenvectors associated with those, bearing in mind that you always want to get eigenvalues of +1 or minus 1, which represent up or down in the alignment that you've got. Whichever way you happen to align this, you will always get a red light or a green light, an up or a down. So you want a plus or a minus 1 as the eigenvalues. The eigenvectors that we identified, and this, remember, this was fully identified in the quantum mechanics concept series, which is why I'm going over it quickly now. Up was represented as 1, 0. Down was represented as 0, 1. Right was represented as 1 over root 2, 1 over root 2. Left was represented as 1 over root 2 minus 1 over root 2. In was represented as 1 over root 2 I over root 2, and out was represented as 1 over root 2 minus I over root 2. And those were the 6 values. The eigenvalue for up was +1, the eigenvalue for down was -1, eigenvalue for right was +1, eigenvalue for left was -1, eigenvalue for in was +1, eigenvalue for out was -1. And all of this fitted into the general formula that the operator Sj, where Sj is either Sx, Sy or Sz, up here, Sx, Sy, Sz, the operator acting on the state psi, which is one of these states here, gives you back the eigenvalue, which is either +1 or -1, times the same state. That was again all covered in quantum mechanics concepts. Well, that was fermions. That was particles that have a spin of 1/2. And you can either get +1/2 or -1/2. What about bosons, like photons? Well, they have a spin 1. which means that there are 3 possible measurements that you can make. We call those plus 1 h bar, 0 and minus 1 h bar. And you'll notice that once again the gap between them is h bar because angular momentum comes in units of plus h bar or 1 h bar. And the eigenvalues of measuring these will be plus 1, 0 and minus 1. So we're going to need spin operators, which are the measurables, and we're going to need eigenvectors, which will deliver us eigenvalues of plus 1, 0 and minus 1 to represent the 3 possible spin states of a boson, which is of spin 1. And I can tell you that you can't do that with a 2x2 matrix. So the spin states for a boson along the z-axis turn out to be 0, I, 0, minus I, 0, 0, 0, 0, 0. That's the z spin state. The y spin state is 0, 0, I, 0, 0, 0, minus I, 0, 0. And the z spin state, sorry, the x spin state is 0, 0, 0, 0, 0, I, 0, minus I, 0. Those are the 3 spin operators for bosons which have spin 1. And the idea is that you take the spin operator Sj, which is x, y or z, act it on the spin state, and that gives you a value lambda times psi. That is the usual equation where we have an operator acting on a state gives us an eigenvalue times the same state. So I've just given you the values of the operators x, y and z, and I've told you that the eigenvalues must be plus 1, 0 or minus 1. So now we can establish what the eigenvectors have to be. And I'm not going to do this for all of them. I'll just show you the principle of how it works. You can do them for yourself. So I'll take the operator Sz and I want us to get the eigenvalue plus 1. So this is when we measure along the z-axis and we want a plus 1 h bar measurable. So essentially we're going to need to take the Sz operator, which is going to be 0, I, 0, minus I, 0, 0, 0, 0, 0. That's the operator. And we're going to have to act on an eigenvector. What is the dimension of the eigenvector? It must be 3 dimensions because we've got a 3x3 matrix. So let's just call that alpha, beta and gamma. Don't know what that is yet. And that is going to produce an eigenvalue, which I've said I want to be plus 1 for this illustration. And that obviously has got to be equal to, multiplied by the same eigenvector, because that's the whole deal. But what do you get if you multiply this matrix by this eigenvector? Well, you're going to get 0 times alpha plus I times beta plus 0 times gamma. So that's going to be the top term is going to be I times beta. The next one is going to be minus I times alpha plus 0 plus 0. So that's minus I alpha. And then you're going to get 0, 0, 0, 0. So this has got to equal this, which means the 3 terms must be equal. So let's see if I can write that out. That means that alpha has got to equal I beta, because that's the top term in each case. Beta has got to equal minus I alpha, because that's the second term in each case. And gamma equals 0, because that's the third term in each case. So we've identified gamma straight away. That's 0. And I can tell you that there are several solutions, but they are all the same kind of solution. But it works if you have that alpha equals 1, beta equals minus I, and gamma equals 0. So consequently, the actual eigenvector is 1 minus I and 0, and that is the eigenvector of the spin operator measuring along the z-axis that returns a value of +1 for the eigenvalue. This is not quite right. Why is it not right? Because if you work out the total probability, these are all probability amplitudes, remember, you square them, or more accurately, you multiply by their complex conjugate, and then add them all together, and they have to total 1. If you do that, you'll get the total 2. So that's no good. So the way we solve that is you have to divide each of these terms by the square root of 2. You don't have to divide 0 by the square root of 2 because that is 0. So technically, you need to divide by the square root of 2 to what's called normalise this term. So for Sz, and with the eigenvalue +1, we've just shown that the eigenvector is 1 over root 2 minus I over root 2 and 0. I can tell you that if you wanted the eigenvalue -1, the eigenvector would turn out to be 1 over root 2 plus I over root 2 and 0. And if you wanted the eigenvalue 0, which is the third possible spin state, then the eigenvector would be 0, 0 and 1. So those are your three eigenvectors for your three separate eigenvalues +1, -1 and 0, all associated with the Sz measurable or operator. And you'd need to do the same calculation again for Sx and Sy.